Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in the Department of Computer Science and Engineering in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the graph traversals. So normally the graphs traversals are going to be classified into two types. So very first thing is that BFS and DFS. So BFS is nothing but breadth first search and DFS is nothing but depth first search. So what is breadth first search? So breadth first search traversal of a graph produces a spanning tree as a final result, and this spanning tree is a graph without loops, and we are going to use this Q data structure with maximum size of total number of vertices in the graph to implement the BFS traversal. So breadth first search traversal of the graph is going to be produce a spanning tree as a final result. So whenever I'm going to have a graph like this, so this graph is going to be generate a spanning tree in such a way that so it is going to be visit all the vertices of the graph by exactly once. So without repeating like this. So the final should be this. So this should be one of the minimum spanning tree of the graph G here. So spanning tree is a graph without containing the loops and all also. And I'm going to say this why how can able to implement this breadth first search. So this breadth first search can be implemented by using the concept of Q data structure. So by considering the number of vertices in the graph to implement this. So what is the algorithm you have to be followed for this breadth first search? So initially define a queue of size, total number of vertices in the graph, and then select any vertex as a starting point for the traversal and visit the vertex and insert it into the queue. So initially define a queue of size, it would be 5, and select any vertex of the graph traversal and then visit the vertex and insert into the queue, that is PA. And visit all the non-visited vectors, so it should be the front of the queue, and insert them into the queue. And similarly, when there is no new vertex to be visited from the vertex, so which is at the front of the queue, then delete the vertex. And repeatedly repeat these steps until the queue becomes empty here. So whenever the queue becomes empty, so then produce the final spanning tree by removing the unused edges from the graph. So whenever I'm going to implement this breadth first search, so few data structure is needed. So for that, uh, initially have to be defined a queue and total number of sizes, and select the vertex as a starting point, and then visit the vertex and insert into the queue. So visit all the non-visited adjacent vertices of the vertex, which is front of the queue, and insert them in the queue. When there is no new vertex to be visited from the vertex, then which is at the front of the queue, then delete the vertex. And repeatedly repeat the steps 3 and 4 until the queue becomes empty, and then whenever the queue becomes empty, produce the spanning tree. So let us consider an example how we're going to implement this breadth first search. So this is the initial graph. So for this, what I have to do is select a vertex as the starting point. So I'm going to choose this vertex A as the starting point, and and insert the starting point of vertex into the queue here. So this is the initial steps we have to be considered for implementing this breadth first search. And the second step is that so visit all adjacent vertices of A which is not visited here. The vertices which are adjacent to A is that A, D, E, B, so which are not inserted. So that's why what I'm going to do is, so have to be insert the newly visited vertex into the queue and delete from A from the queue. So A adjacent vertices will be D, E, B. So these things I push move on to the stack and delete the vertex what is there, that one is deleted here. And comes to the third step, so visit all the vertices of next one. So visit all the vertices that are adjacent to D, which are not visited, and then simultaneously push onto the queue and delete that vertex D also. So the vertices what are visited adjacent to D is A, B, E. So B, E already is there, A already visited, so the vertex D are also deleted here, and this should be the result of the queue contents. And next one, so what are the adjacent vertices that are adjacent to E node? E is that, so B, C, and F. So this one B is already there, so I'm going to push C and F. So the vertices that are adjacent to uh, E. So what is the vertices? B. So B is already is there. No need to push. And up next adjacent is C, and then F. I'm going to push onto the Q. So next one. So next value in the Q is B. So what are the adjacent nodes that are adjacent to node B? Is that C, A. A is already visited. E already visited. So the node B is just simply deleted here, and the contents of the queue should be Q and F only. And what are the adjacent nodes that are adjacent to node C is this. So B is already there, E already there, then F, and then G is there. So F is already there. Next, I have to push G here. Then finally, the adjacent vertices of F is that G and C. So G is already there, so C already visited, and simply delete the F also. And finally, we are going to have G. So G adjacent vertices should be C and F. So C and F already visited, so simply delete G also. So whenever the queue becomes empty, that path what we traced till now, that should be this new spanning tree, right? So like this, we are going to be implement the breadth first search by using the queue data structure. So here in the current example, so initially have to choose a starting point vertex, and that one is going to be pushed onto the queue. So when that one is visited, the vertices that are adjacent to A is going to push onto queue, and we have to be delete that node A. And the next step, what we have to do is, so what are the vertices that are adjacent to is going to be identified, and those things is going to push onto the queue. If already is there in the queue, then leave it, and the remaining nodes what we not visited, that should be pushed onto the queue. And next one, so like this, we have to be repeat all the steps and until the queue becomes empty. Whenever the queue becomes empty, so the path traced till now should be the BFS order. The next one is depth first search. So depth first search travels of a graph going to produce a spanning tree as a result. For implementing this, we need a stack data structure here. So for BFS, we need queue data structure, whereas depth first search we need a stack data structure. So with maximum number of vertices in the graph. So the DFS traversal of the graph is going to produce a spanning tree as a final result. So what is the algorithm we have to be followed here? So the step one is that, so initially define a stack of size total number of vertices in the graph, and second step, so have to be select any vertex as the starting point from the traversal and have to visit the vertex and push onto the stack. And third step is that we have to visit any non-visited adjacent vertices, so which is at the top of the stack and push onto the stack. And step 4, we have to be repeat the steps until no new vertex is going to be visited from the vertex which is at the top of the stack. And next step, so whenever there is no new vertex to visit, then we have to use backtracking and we have to form the contents of the stack. So repeatedly, we have to repeat the steps 3, 4, 5 until the stack becomes empty. So whenever the stack becomes empty, then produce the final scenario by removing the unused edges of the web. So note you have to be remember is that backtracking is coming back to vertex from which we read the current vertex. So for implementing this DFS, so initially you have to need a stack, and then based on the size of the size of number of vertices in the graph, and select the and choose any vertex as the starting point, and you have to visit the vertex and you have to push onto the stack. And third step is that, so visit any non-visited adjacent vertices and you have to push it onto the stack. And step 4 have to be repeat the steps 3 until no new vertex is to be visited. And whenever the no new vertex is visited, then use backtracking. And step 6 is that, so repeat the steps 3, 4, 5 until the stack becomes empty, and finally pursue the spanning tree. So let us consider the same example, then how I'm going to consider the DFS here. So for this I'm going to choose this A as the starting vertex, and I'm going to push A onto the stack here. Then, so what are the adjacent vertices of A is B, so I'm going to choose B and D, so but I'm going to choose only one, so um, instead of D, E, B, so I'm going to choose only one vertex, so that's why I'm going to choose B here. So the B is going to be pushed onto this stack. So for B, what are the adjacent vertices is that, so A already is there, E and then C. So I'm going to choose C here. So C is going to be pushed onto the stack. And C, if I'm going to take, so what are the adjacent vertices for C is that B, E, C, and F and G. So for this, I'm going to choose E here. So I'm going to push E onto the stack here. And for E, what are the adjacent D and then F? So I'm going to choose D. So D should be pushed onto the stack. So since this should be reached the end, and so what I'm going to do is, so I'm going to apply backtracking. So again, I have to come back here, and then what I'm going to do, so again I have to apply whatever the next vertex I have to visit, that should be F. So the F is going to be pushed onto the stack. So for F, so what I'm going to do, I have the adjacent vertex is G. So G is reached, so G should be pushed onto the stack here. So since G should be the dead end, so I have to apply backtracking and I have to find whether any non-visible vertex is there or not. You have to be do. Right. So from G onwards, so I have to come back. So no element found. For F, also I have to come back. So no element, no non-visible vertex found. And again from E again I have to go back to C, and from C it again I have to reach B and B to A. And finally remove the non-visited vertices. finally the graph what we are going to have, that should be the minimum spanning tree. So like this we have to be construct the spanning tree of the graph here. Okay, so let us consider. So normally this breadth first search and depth first search should be little bit uh, able to produce the same resultant set, but only the algorithm may be different here. So in depth first search, what I'm going to say, so in breadth first search here, so let us consider simply I can able to extend by considering example. Breadth first search I'm going to take, so A, B, C, D. So for breadth first search, what I'm going to do is, what are the adjacent vertices of B, A, B, so A, B, C. For B, what are the adjacent vertices? A already visited, so D is there. And C, what are adjacent vertices? D, so nothing, so already visited. So this should be the BFS order. So what should be the depth first search? Depth first search is that we have to choose only one. So A to B and B to D, D to C. This should be the BFS order. So what I have to do in breadth first search is that, so I have to choose the starting point and push the element on the stack. So what are the vertices that are adjacent to A, that should be pushed on the stack and remove vertex. So repeatedly have to apply this concept until the stack becomes empty here. When it comes to depth first search, so if I'm going to consider the graph like this, so what should be the BFS? So what are the adjacent nodes? A, B, C, D. And if I'm going to consider B, what are the adjacent vertex? E. And for C, it should be F. And for D, it should be G. So this should be the BFS order. And what about the DFS means that? So DFS means A to B, B to C, B to E, A to F, F to C. So look this one, again come backtracking, and F to G, G to D. So this one is different and this one is different here. So here I'm going to use Q here, I'm going to use stack here. So initially how to do? So initially how to choose the vertex here, that thing should be pushed onto the stack, and what are the adjacent vertices? Either one you have to consider, that one is going to be pushed on the stack. So here B I consider, so that one I'm going to consider B. For B adjacent is C, I'm going to take, so C on the push onto the stack. So for what are the adjacent vertices for C, E, F and G, but I'm going to consider E, and that one push onto the stack, and again have to find D also adjacent one, but already it reaches the dead ends, or otherwise it is going to get the cycle. So that's why I have to apply backtracking here. So again come back and apply what are adjacent nodes for F, so G, so all the red lines is going to indicate the backtracking. And finally this should be the result in the spanning tree. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.